Okay, mic works. Okay, thank you everyone for coming. My name is Christine. I'm a PhD student at Carnegie Mellon University, and I will be presenting my work that I have been doing with my colleague at the ERCOT National Laboratory, as well as my advisor at CMU. Okay. Yeah, so we are currently in the middle of an green energy transition. As we are looking to decarbonize our grid, we're moving away from the more fossil fuel-based generation technologies into the more renewable generation technologies. But as we introduce more renewable technologies into the grid, these technologies are heavily weather dependent. So when we model this process, we assume what is quote unquote called a typical weather day for grid operations so that we can assess how we plan our grid in the future. But as we're seeing more and more impact with climate change, our definition of what is considered typical is rapidly shifting from 10 years ago to now to 10 to 100 years in the future. So the rapid shift in our definition for typical weather impacts how we are planning for our future capacity on the grid. And if we underplan or overplan for our future grid, it actually leads to a lot of resource adequacy concerns, which then leads to grid reliability concerns. So FERC defined grid reliability as provision of an adequate, secure, and stable flow of electricity as the consumers may need it. And resource adequacy is one of the two key tenets of grid reliability, being the ability of the electric system to have sufficient generation to meet the demand of consumers. So under this scenario, when we introduce more wind and more solar into the grid, we have to be able to account for resource adequacy in addition to our grid decarbonization. So currently, we use a class of models, power system models called capacity expansion models to do this grid planning. But capacity expansion models are using historical weather data, which doesn't fully capture the uncertainty of future climate impact as we are projecting into the mid-century or the end of century. So I currently have access to this future weather forecast, and we are looking at ways in which we can bridge the gap between future climate modeling as well as projecting out our power systems planning. So my work asks the question, what is the impact of representative weather period selection methods on capacity expansion decisions in the mid and end of century? So the input data pipeline for capacity expansion modeling looks like this. So we'll start with the weather data. Weather data, we have wind speed, global horizontal irradiance, which is GHI, and air temperature. So this weather data translates into the variable renewable generation data, being the wind generation output, the solar photovoltaic output, and the load, all of which has a specific type of model that translates the corresponding weather variable into the renewable generation data. And this renewable generation data is what is being fed into the capacity expansion model. And I'm going to plug our in-house model, the Argonne Low Carbon Electricity Analysis Framework, ALEAF, which is what I'm using for this study. So I have a slide on it. I think the next one, there we go. So the ALEAF is is a pretty comprehensive analysis framework that centers on designing future grids for decarbonization, for reliability, and for resilience. There are a whole host of things you can do with it, but I mainly use it for the climate and weather data analysis part. And I do want to point out that it is highly spatially resolved for the US electric power grid, especially for Texas ERCOT, where we have it down to county level resolution. And that is why we are doing the case study for Texas ERCOT. So I talked about the data pipeline, which is translating this weather data to the variable generation data, but getting this to all the way down to the days that we're going to use for any future weather year to model the grid operation has several more steps involved, as hinted by this mostly blank slide. So from the variable generation data, we have to first perform a spatial reduction to reduce the number of physical spatial locations we are considering, even within, say, like the state of Texas. And then from spatial reduction, I have formatted it into a 2D flattened format where every row of the data contains all of the data for one single day in the future. And from that point on, I did a principal component analysis to reduce the number of dimensions. And then from that point on, I used the K-Meadows clustering method to select for the number of any number of representative days to feed into the capacity expansion. So I primarily consider the K-Meadows and dynamic time warping method because it is quote unquote the state-of-the-art method, and it is also generally pretty fast if you also perform dimensionality reduction on top of it. But I'm also interested in assessing my ability of using a fuzzy clustering method to compare the difference between the methods. So the main difference between a hard and fuzzy clustering methods is that given a data set, so hard clustering will assign a definitive membership to each of the points. So if your point A belongs, point 1 belongs in cluster A, it does not belong in cluster B. However, for fuzzy clustering, it assigns a probabilistic score for each point relative to the cluster assignment. So point 1 can have a 70% chance of being in cluster A and then 30% chance in cluster B. So that probabilistic assignment would allow us to assign an uncertainty weighting to each of the representative days we select, so that when we use it in the capacity expansion modeling, we can translate some of that uncertainty from the data selection into the feeding it into the uncertainty of the modeling. So the data set I've been talking about, that raw weather data set, comes from the Argonne Climate Risk and Resilience Portal, or CLIMER. It is a dynamically downscaled output from 3 different global climate models. And for all 3 global climate models, it's at a 3-hourly time resolution for all of the weather variables, and a 12-kilometer by 12-kilometer grid covering most of North America. But what the team has also done has been, they interpolated the time series into hourly resolution, and they also selected the data for just Texas, I think mostly for my team's convenience. And the results I'll be presenting on later, and this study in general primarily uses one of the 3 climate models. So I'm using the Geophysics Fluid Dynamic Laboratory, or GFDL's global climate model. And we are considering this greenhouse gas scenario of RCP 8.5, which is the very high emission or the business as usual case, if you're familiar with the IPCC reports. And we are looking at mid-century, which is 2045 to 54, and end of century, which is 85 to 94. And I briefly mentioned this spatial location selection. And this is what it looks like on the Texas ERCOT map. So we performed this spatial dimension reduction and reduced all of our data to one location, which is a 12-kilometer by 12-kilometer block per county per weather variable for the Texas region. And now what I will be presenting results on later is the temporal resolution reduction piece, which is a little bit more tricky because I want to compare what methods work better and how many representative days do we actually need to be able to capture this annual weather variation on variable generation capacity like forecasted into the future. So the whole point is that we should be able to use a representatively selected sub-data set, and the result of it should be comparable to using the full high-resolution spatial temporal data for capacity expansion modeling. So this is the flow chart of the full workflow of the experiment. So in order to perform this impact assessment on representative sampling, we have the selected representative locations, feeding it into the clustering algorithm to get the representative time periods, feeding it into the capacity expansion model, and then generating results for the mid-century and end of century. And I'm also similarly going to look at an alternative clustering method to get the representative days. And both of these methods will actually be benchmarked against the method that's already internal to A-Leaf for selecting representative days, which is it's called scenario reduction, and it's a tree-based method rather than a clustering-based method, if you're all familiar with that. So just going over some of my preliminary results. Running one weather year takes a really, really long time, and because it's a very complex optimization to solve. And so I've only done it for a few years in the mid-century so far. And hopefully we will have all of the results by the end of the month. So I just want to quickly go over a weather data visualization so that we can have an idea of what it looks like in Texas. So this is a couple days in January in the year 2050 for the GFDL model for the business as usual case. So we see that air temperature fairly cold, but not too cold because it's still Texas. And we see that in terms of PV output, you're seeing high amounts of PV output potential all over the state. But for wind output, it's generally more focused on the western, the northern part of Texas. So in this experiment, we are doing a greenfield expansion, and I'm considering 6 technologies. So first, the thermal options of NGCT, and which is combustion turbine, and NGCC with carbon capture and sequestration. For the variable options and considering onshore wind and PV. And then for storage, I'm considering LFP batteries at 100 megawatt hour, 100 megawatt 4-hour duration, and pump storage hydro at 100 megawatt 10-hour duration. So we are not considering any long duration storage in the study. All right, so I showed the picture of Texas a few times. But for this study, we are starting at a high spatial resolution, which is the county resolution of the model, and we are actually aggregating it up to the weather zone spatial resolution. So there are 9 weather zones in the Texas ERCOT region as defined by ERCOT themselves. And we did this aggregation mainly to make it honestly easier to solve the optimization. All right, so this is in the year 2045, which is the first year of the mid-century. So we see that this is a faceted breakdown of all of our investment technology, as well as the installed capacity per technology for each combination of the number of representative days used and the selection, the methods in which, the methods of which how I got those days. So left half is the K-meadows clustering method, and the right half is the scenario reduction method that I'm benchmarking against. So I do want to note that in 2045, there are actually no investments in pumped storage hydro and combined cycle with CCS. So this, I feel like, is a more intuitive graph to look at. So this is the difference in installed capacity from what I call the baseline case, which is 365 days for scenario reduction. I consider that the installed capacity using this setup is the, if we have perfect foresight, so this will be the truth. And all of the, and the rest of the data we see on this figure are the difference that deviates from the truth. So again, no pump storage hydro, no CC with CCS, but we see that for the clustering method, it actually over-installed onshore wind, and it under-installed PV. But for the rest of the scenario reduction method, outside of the baseline case, it consistently over-installed PV, and consistently and very significantly under-installed onshore wind for the year 2045. And this is what it looks like. The same idea, same difference graph for 2046, 7, 8, and 9, so the first half of the mid-century. Unlike 2045, the rest of the years shows like an opposite pattern. So we see that actually K-meadow clustering generally led to pretty systematic over-installation of onshore wind and under-installation of PV. But scenario reduction showed, it's less observably consistent, but it also led to less difference in the installed capacity from the baseline. So from these figures, we generally want our results to be as close to the baseline truth case as possible. So from these, we would argue that the scenario reduction, so the method I'm benchmarking against, is actually better than the method I'm testing. And what I find generally interesting is that if we also use these figures to find out how many representative days we need in order to do the capacity expansion for future, we want as many days as possible, right? Like as many days as possible, we get, generally we get data that are much closer to the quote unquote truth. Let's switch gears for a bit. So in data science, there are data science methods that will help us select the number of the ideal number of clusters when we do this type of this type of clustering. So I'm using something called the silhouette score to assess my results. So a silhouette score is a measure of cluster quality from -1 to 1. And you generally want to select a number of clusters with the highest silhouette scores. So based on this, in the year 2046, selecting 70 days, it would actually theoretically give me the best results. And then for 2047 is 90, for 48 is also 90, and then for 49 is 130. But if we compare what we saw here with the results from the capacity expansion, they are quite contradictory. So so this is one of the main points that we are arguing, in that using data science methods alone to do this type of representative day selection may not actually lead to the desired or expected results, especially when we are considering forecasting into the future, as seen here, where the data and the pattern within the data is does not translate well once we want to tie it closer to the grid. So this is just I included this because I like this figure. It's a fun figure. It's the onshore wind capacity factor in percentage of the selected representative days. So the top two are in the year 2045, and the bottom two are in 2049. And what we saw here with this systematic over-installation of wind, especially for the year 2049, you can actually see in the third figure that the algorithm is picking more and more days with higher capacity factor compared to the scenario reduction method in the fourth figure. So similarly here, this is the PV capacity factors, and in contrast to the previous one, which was wind. And this one is harder to tell because of the coloring, but the systematic under-installation of systematic under-installation of PV can also be seen in the 2049 case from figure 3 in contrast with figure 4. So I want to make a general comment on the trends we saw in the first half of the mid-century decade, is that there's really no clear change in pattern for installed capacity for each technology, fully keeping in context that we did a greenfield expansion. So I want to point out that there are no investments in pump storage hydro or combined cycle with CCS in any of these years. And am I cutting close to time? Okay, all right, I think this is the last figure, I promise. Okay, so why do we care about this? If you can run the 365-day truth, why not just always run that and you'll just get the truth every year? So all of this long list are every step it takes to run a capacity expansion model. And we can see that all the way on the right, the truth case takes significantly longer to solve than every other case. So this is why it's infeasible, because the model runtime grows exponentially with the additional days. So it's truly just not feasible to do that, to always get the truth case, especially when we want to consider long duration storage. That will require us to optimize for a number of days per period, which makes the optimization even more complex. All right, so in conclusion, no investment in pump storage hydro and CC plus CCS. There are clear differences in installed capacity due to the difference in representative day selection method with this annual variation. And clustering, we saw systematically overinstalls onshore wind and underinstalls PV. And my next steps are to add the representative days and run the capacity expansion modeling for the fuzzy method, as well as run it for the end of century, and analyze the variability across the 2 decades. Argonne's lawyers told me to put this up. This is funded by the government as well as a National Science Foundation. And thank you very much.
So just one, thanks a lot for the presentation. Just one question on the model that you have mentioned, the A-leaf, and also one of the models on risk and resilience. I was wondering if these models are they open source?
We are. Sorry, I'm just scrolling back to that slide. We are in the process of making this one, right? Yeah, we're in the process of making it open source. If you actually just search up this on the bottom.
So there is already a paper.
No, that's a citation for the slide. But there's a web page on it, but the actual model itself is not open source yet. So we're trying to make it open source. And specifically for the risk and resilience, we just made an RA like a RA model extension to A-leaf. So that one is in the review stage. The paper is, yeah.
So within you have some result about overinstall and install and also comparison of. So I do have like the kind of target for that. What stage you feel like the accuracy or the simplification of the representative data is good enough to have a balance between faster computation and sufficiently good results.
Yeah, so I am currently looking at improving the algorithm for the day selection itself to get the over installation within I'm using 10% as kind of my target, like within 10% accuracy of 10% difference of the base case I talked about.
No question, like some speaker.